So what I want to do is frame up a problem. I've gotten up here a few times now, spoken about Netflix and what we've done over the past couple of years for deploying infrastructure. What we haven't really talked about is how does this take us into the next decade, both from a technology scale perspective and from a technology cost perspective. Let me introduce our panelists who are going to speak about this. Wait, this is a way old version of this deck, I think. No? Okay, we're fine. We're fine. Sorry. So I had the last version, I removed Mark Burley from Arista. He, unfortunately, because of travel, was going to come in yesterday morning and his flight was proactively canceled. I'm Dave Temkin. I work for Netflix. Up on the stage, we have Craig Pirantazzi from Microsoft. If the original version of the talk that was posted had VJ Gill, yet another travel casualty, but we're happy to have Craig. We have Mr. Richard Turkbergen, or Steenbergen, depending on the poll results that will be announced later on, from GTT. We have Kevin Wallenweber from Cisco. And a last-minute addition, you just heard Russ speak. He might have some good insight as well for the panel, so kind of standing in for Mark. Mark. Oh, it's that kind of morning. So I want to be clear about one thing. This panel, there's a reason why we have Cisco up here, and we originally were going to have Arista up here. I invited Juniper to speak up here. This is not to attack vendors. We're not saying your stuff is too expensive in that your margins are too high and how dare you charge as much as you do and yada, yada, yada. This is a technology problem. We think vendors can help us one way or another. And so what we really are focused on here is figuring out what the long-term answer is depending on what buzzwords we want to apply to it. This is not in any way specific to any vendor. And I really do thank Cisco and now Ericsson for coming up here. So from a background perspective, we began our project where we installed our big expensive routers approximately 2 years ago. We've got about roughly 100% of our traffic just below that on our own platform at this point. We've rolled out at this point 18 terabits of network and server capacity around the world. A quick map of where we are. So this is a scale drawing of one of my colos. You may have heard of the internet and you may have heard of House of Cards, and then there's also the content that you'll at some point today complain to me about. There's not actually a lot of complexity here. In reality, that's what it looks like. So it's a big expensive router in the middle of some transit and some peering and some servers, and that's really it. There's multiple of these, right? The scale is really just how many of these we deploy. And that's where the cost driver is. Things like power and space and the actual hardware is what drives the cost and the complexity. So we recently, since the last time I presented in front of the NANOG crowd, introduced an even more dense platform for delivering bits, which means that I can deliver 40 gigabits of traffic, nearly 40 gigabits of traffic from 1 U of rack space. If you think about that, and I can fill a rack, 150 watts a piece, I can fill a rack at 8 kW and end up with over a terabit out of a rack. That's pretty crazy. So the scale itself is unprecedented, right? One of these clusters, I need to be able to deliver 640 routed 10 gig ports. Now this is, again, the big expensive router construct, right? Not the, I've come up with some awesome little cheap box, that can, I can only put certain routes into the fib and play games of policy and have an RSP that's way too slow to deal with updates in a meaningful amount of time. This is, I want a performant network. And if you think about the current products on the market from the major vendors, 640 10 gig ports is at the way upper limit of what any of them can fit into a single chassis box before you start talking about defining chassis as entire cabinets that then connect to each other. So this isn't optimal in numerous ways. Routers are really expensive, right? We're talking about $10,000 to $15,000 per 10 gig E at list. You know, and we can argue about who pays list for what, but the overall point is that if you really take that price and multiply that by 640 ports, that's an awfully expensive rack of ports. These boxes do lots and lots of things that I don't need them to do, right? I don't need MPLS in my case, right? I don't really need layer 2 VPN. There are certain use cases. I've got an awesome network architecture team that can come up with all sorts of great ways to turn on knobs for things if we really wanted to do something cool, but in reality, we don't need it. There are things that they absolutely need to do. They need to route packets. They need to route IPv4. Sometimes they might need to route IPv6. I don't need to run these, though, like a data center. I'm almost one-to-one. My server can put out almost 40 gig, so I don't have the opportunity to build a big aggregation layer. On top of that, my application is really smart. My application can make a lot of decisions regarding how and where to serve traffic from, to the point where our application takes a BGP feed in today to make a lot of the decisions it makes. And so if I've got that, I don't really need all sorts of added intelligence on the edge. Now, if I wanted to, that server that I just showed you and our other servers that we've showed off before, I can build 90% of that from off-the-shelf parts at Fry's. I can walk into Fry's, I can buy a bunch of hard drives, I can buy a motherboard, I can buy a few SATA controllers, and effectively build what we call an Open Connect appliance. I can't do that with the router. I mean, it would be really impressive. Someone should Photoshop a bunch of Linksys in a 48U rack. But in reality, I just can't do that with the router. And so we recognize that just from a cost perspective, you're never going to have true parity, and nor are you ever going to truly follow the Moore's Law curve in routers like you do in servers. And on top of that, these boxes are getting harder and harder to cool, right? We've gone from basically having a 5 kW rack be more than enough to deal with whatever router you could throw at it. Now we're up in the 10 to 12 to 15 kW range. People are talking about water-cooled routers. That idea to me is insane. And, we've talked about, if any of you were in the data center track the other day, the question came up regarding water-cooled server racks and the added complexity there. Could you imagine that if you needed to do anything to your router, you need to have a chilled water loop running to it, and you have to have your data center deal with any piece of maintenance to do with your router because of that chilled water loop? I think I'll pass on that. So how do I bring this all together? If you think about a router, it's actually really terrible at making decisions for routing traffic. It's not really a good routing engine. It takes a fixed set of inputs for things that change drastically over time and applies the same calculation to it no matter what happens. This is not the way forward here. We've added extensions onto things. We've started talking about segment routing, right? Segment routing is great. It's a good concept. It helps us. It takes some complexity out of the network, allows us to build maps of what the network should look like offline. That's great. However, we're still just kind of putting a Band-Aid on what already exists. We're not really seeing the innovation at the edge we'd like to see. And when you think about what a router is doing, none of what it looks at has anything to do with the actual performance of a path, which is what most of us, at least in the content world, are concerned with. And so how do we get that performance info into these big shiny boxes? Or how do we get away from these big shiny boxes? If you think about it, my network is way greater than 50% of my server cost. I don't need MPLS, I don't need carrier Ethernet, I don't need IPv6. Anyone? No? I don't need layer 3 VPN, and I don't even really think I need a full scale fit. So I posed this question, but I'm going to actually wait, let the other panelists present first, and then we'll hopefully have an interactive discussion with the audience about that. I'm going to ask you to not use buzzwords like SDN, big data, the cloud, or big data in the cloud. And so if you could just avoid those in all of your responses, that would just be fantastic. Thanks. We get the next deck. Thanks, Greg.
How you doing? We're not allowed to use those words either, so I had to redo my slides because they all said SDN and cloud and everything. So I'm Craig Parentazzi, Director of Network Engineering at Microsoft, and a poor VJ Gill substitute. But I did want to channel VJ a little bit and start off with our COGS. Our COGS is too damn high, and it's all Kevin's fault. But Kevin will be up here, and I don't envy Kevin's job at all, actually. We're all telling him to build different things and strip this out and put this in and make it bigger and make it smaller and make it faster, make it slower. So I don't know. His head's probably spinning by the time he actually gets a PRD over to his engineering group. So, okay, the Microsoft network. So 8075 is the public-facing network, and it's delivering bits to the end user. Its general function is just to deliver services, to terminate them closer and closer down to the consumer. So today, that's pretty much what it looks like. It's a global network. It's N by 10. We are moving to 100. The public-facing network is pushing probably about 5T right now. It is a feature-rich network. It's an IP MPLS network with multiple MPLS meshes on top of it, a best effort mesh, a priority mesh. We are using auto bandwidth. We're using forwarding adjacencies. It's a pretty complex network at face value when you actually dig into the configuration itself. One of the interesting things about it is each of those dots is obviously representing a market or a city, but within each of those markets we can have as many as 5, 6, sometimes even more facilities in that market, in that region. So the complexity from a scaling perspective is not only the wide area here, but it's also intra-market. So we're delivering terabits of capacity between facilities, whether it's intra-campus, intra-data center, and those can be anywhere from across a parking lot or across the street from one another to on the other side of a city or a market. Some of our larger properties traffic profile, especially on the cloud services side. Sorry, I used cloud. We get requirements from our product guys, our services guys, that say, machine to machine can't be more than 1.8 milliseconds. Machine to machine can't be more than 0.7 milliseconds. So that's how we're designing each of these markets as we scale different generations of data centers into the markets. We do have another network, which is 8074. It's private, and that's our inner data center fabric. It's our inner data center network. So that's where it's just big fat pipes between the major data centers for things like moving around the Bing search corpus, BCDR, data replication, Exchange Online, SharePoint, moving around big chunks of data, mailbox replication, things like that. Okay, so the topology inside the data center themselves is actually a 3-stage folded cloth, a fat tree. And the advantage we get from this is the horizontal scaling. So a lot of the applications demand non-blocking east to west bandwidth because a lot of the application components are actually spread out amongst a large number of servers. Not only are they spread out amongst a large number of servers, but also like I was saying before, in a particular market, the components of the application actually might be distributed amongst locations within a market. So the machine-to-machine traffic actually might be talking across facilities within either a campus or a region or a market. So we're able to do this obviously with the dense commodity hardware. We're trying to build larger networks out of smaller components, simplify it, reduce the variability on the network, get the economies of scale and the stat mux of a Clos matrix and the aggregation that it gives us with the oversubscription, and then thereby reduce costs that way. So from a requirements perspective, one of the complexities that we have is we have over 200 actual online services that are using the network and using the data centers. So from an application standpoint, we have to take into account a pretty large set of requirements, whether it's the social media, it's the Bing web index and moving around the search corpus, the targeted advertising, the Bing imagery, so moving the maps and the imagery around, the cloud computing stuff, so both the public and private Azure cloud services and CDN, and from that perspective, that gives us a lot of elastic compute and storage requirements and traffic profiles that we need to deal with, and then of course we have the real-time analytics that are going on at all times. So from a requirements perspective, low latency computing, which is leveraging the distributed memory across the nodes. So in general, we see a lot of ephemeral traffic profile, traffic flows across the network. We see a lot of from an east to west traffic profile. That's what's really driving the need for this large bisectional bandwidth that we really have to deal with. Okay, so what are we seeing on the trends? So I think this is going to, Kevin's going to come up here and pretty much, oh yeah, I think he almost has the same graph as we do, which I guess that's a good thing, that we actually see the same thing. So what we're seeing is when we are mapping the costs on the network inside our data centers, we're seeing those costs shift over time from the silicon over to the optics and the cabling infrastructure that we have to put together inside and between all these facilities. So the switching costs themselves in the fabric layer, those are continuing to decline with silicon economics, but we're really not seeing that being reflected, or at least the curve being as steep from a cost compression or unit cost compression side with large feature-rich core routing nodes, routing devices. And then, like Dave said, the power and cooling on these large network elements is a huge problem that we're facing. Even as the power per bit goes down, stacking chips on boards, building larger and larger routing nodes is actually the total power is going up. And when you're getting past 10 kW, 12 kW, it really causes a lot of challenges, not only in our facilities, but in third-party facilities where we're trying to drop these nodes into. So what are some of the things we're thinking about as we're trying to deal with the challenges, not only on the wide area, moving the bits closer and closer to the end users and the consumers through geo expansion, but inside the data center and between the data centers. So first, we're really looking at any optimizations around service resiliency itself. So decoupling the service availability from the network availability and engineer availability essentially from the get-go. So if you start with the premise that equipment failure is a constant operating condition and you look at it as a software opportunity, you can really start to do some interesting things with migrating workloads around under failure and maintenance conditions. Abstract the service itself from the hardware and the protocol stack, and abstract it from any manual processes that you might have to go in, and your NOC is sitting there waiting for an alert, and the red flashy light goes off. Now I got to go fix something. That's adding time to mitigate, time to detect, time to restore. Which is obviously from a user experience and a service availability perspective, not where you want to be The interesting thing about service resiliency in the software and decoupling it from network resiliency itself is then I get to go tell Kevin and his and others that I can actually start stripping down the requirements list and say, you know what, I don't need it to boot really, really fast. I don't need things like graceful restart. When the node goes offline, my workloads migrate. Their traffic engineering is happening at the service level, and then you can boot in 10 minutes, 12 minutes, partial boot, whatever you want. So it really simplifies what Kevin and the vendors actually have to do and think about when they're engineering a box. The trends keep swinging back and forth, what we want and what we're utilizing in the networks. And I think even a couple of years ago, people were like, it has to boot as fast as possible. Please get it back in 30 seconds. And that puts a lot of constraints or a lot of pressure on a box that's 5, 6, 8, 10T router. Spins all its fans up at the same time and chews up all that peak power. So the second thing when we're looking at scale and lowering cost is if I can actually do the first one, I can then do the second, which is increasing scale at lower cost through cheap label switching. I also need lower cost integrated WDM solutions, not only for wide area, where the integration can help with the unit cost on the optical side or the packet optical side, but also in the metros, in the campus environments, where at the border leaf layer of my network, I'm connecting at huge speeds, huge capacities, and I really want this type of low-cost integrated DWDM solution to be on the same depreciation curve as practically like servers, so I can crop rotate not only my servers and my colos, but also crop rotate my WAN and LAN connectivity. So where we're heading is a future where there's much fewer, if not no protocols actually running on these network elements, and all of the path computation is done either offline in some type of path computation engine, and the fib is programmed down into the network, or even at a services engine, if you will. And then you can just dumb down your entire network. You have the same consistent forwarding paradigm through the whole entire network with some type of quote-unquote label switching. And I'm not saying it has to be MPLS, it has to be this or that. It's a cheap label switching solution. And then lower power consumption. We talked about power a little bit. I was talking to somebody in the back, and 10, 12 kW seems to be the sweet spot. So from our perspective, we'll actually trade off density and capacity for the lower power consumption, and then use these smaller widgets to scale a network horizontally. That also gives us the ability to essentially get hardware ubiquity. So I can use similar platforms, same chipsets across all layers of the network. And then essentially what we're asking for is smaller, stupider, and cheaper, but not too small and not too stupid. So I think that's all I have.
Thanks. So next, let's have Kevin go, and then we'll go into Q&A after that. Oh wait, no, sorry. Richard first, and then Kevin. My bad. Not bad.
Hello. I am Richard Steenbergen from Turkbergen Telecom. No, just kidding. GTT. And something. And I'm here to talk about how to make big, expensive routers less expensive, but probably still big. So the reality is that Ethernet can be really freaking cheap if you want it to be. There's a whole bunch of simple hardware out there that's really, really cheap. And the simplest example of this is all of the Broadcom Trident derived boxes that are out there. So take a look at every vendor on the planet essentially is making one of these, rebadging these, selling these, adding their own little twist to them, but it's essentially the same hardware, the same design. You have the Juniper QFX, the Cisco Nexus 3Ks, the Force 10s, some newer Arista boxes, HP Alcatel Loose, and IBM, and literally dozens and hundreds more, including every random Chinese vendor known to man. And the thing that all these things have in common is a very simple Broadcom chip that now delivers massive amounts of bandwidth for ridiculously low amounts of money. So the question then becomes, why is my expensive router still expensive? Or why does my MX960 blade cost a couple of orders of magnitude more than my 1U HP switch? And to be fair, it's not all that your router vendors are just trying to bilk you. A lot of these are very complex technical problems, and especially when you start building these very large chassis and you start trying to design all of these failure mode protections and redundancies, you end up with something that's even less likely to be stable and very complex to engineer. So in fairness, these are very complex technical problems, but then again, sometimes the technical problems aren't always, shouldn't have ever needed to exist in the first place, and sometimes we're beating our head against problems that don't necessarily need to exist. So the answer to why you still pay for your big expensive router is you probably want your big expensive router to do some fancy things that your small cheap router can't do. The real question is it because the box can't, or simply because it doesn't? So here's an example of something that's missing in the product space, the case of core MPLS switching. There's a lot of networks out there that would benefit greatly from a dedicated core that really was dumb. Didn't need to carry a big fib, didn't need to do deep packet processing, anything. All it needed to do is MPLS switching. And in terms of hardware, it's actually ridiculously easy. In fact, that was one of the reasons that MPLS was designed in the first place. You're doing simple exact match lookups, you have very little state, there's very simple headers to parse, you need a very small fib. There's all kinds of reasons why the hardware could be able to do it better. And in fact, a lot of the commodity hardware that's out there today actually can do it. So the question is, where's my cheap MPLS only core platform? If you look at a platform like Juniper, since they're not up here to defend themselves, the PTX is really barely any better than the MX in terms of density, in terms of price, in terms of, that's not an order of magnitude savings benefit. It's not anything that really motivates you. So the question is, why do I need to buy this $1 million core box if I could do something like that with a $1,000 cheap box and the hardware can support it? So the answer in this particular case is because all of these other cheap boxes don't have the software. It turns out that doing MPLS is really simple in hardware and actually pretty complex in software. You think about all the work that goes into signaling, bandwidth reservations, doing all the fast reroute, all these different mechanisms out there. Really only the incumbent router vendors actually understand it, and that's because they're the ones that wrote it. So you see other vendors try to come along. You see Brocades and the old Foundry boxes and people that try to implement it, and they do to some extent, but they don't do it to the full carrier grade suite of a Cisco and a Juniper who actually wrote the protocol. That's really the reason you don't see any type of box in this space. So why would Cisco or Juniper make a cheap, dense 1U MPLS core box with a 64 by 10 gig solution? They would just be cannibalizing their own carrier business, and there's no competition in the market. And like Dave said, we're not here to bash on these guys, but we're also here to look at where are there areas of improved competition, where are there ways to solve the problem in non-traditional ways instead of just trying to throw more power and rack space and cooling at it. So, SDN Big Data Cloud Hadoop. Sorry. To the cloud. But before we fire up the hype machine, let's talk about what actually is SDN. What is software-defined networking? Because it's one of those things no one actually has a real grasp of what they're actually talking about or claiming they're talking about. So the reality is I've been using software to define my network for quite a while, and if you haven't, you've probably got a lot of unmanaged switches. That's probably not a very interesting network. So is SDN just another fad, or as Avi Friedman would say, a funding augmentation device, which in a lot of cases seems to be the case, or is there actually something that could be accomplished with that? But first, I think you want to talk about what did you actually spend your money on when you buy your big expensive router? The reality is there is no big expensive router. What you actually spent your money on, blowing your mind without CDP or MAC addresses, if you have hardware that can forward all of these packets and do it so cheaply and so commodity and all of the features are there, what you're actually buying when you buy these big expensive routers is software. Turns out software is actually pretty hard. all the complexity that goes into all of the routing protocols. And it's not just one simple routing protocol and one simple networks. It's all of the design that goes into routing protocols that are built to scale to thousands and tens of thousands of nodes and not fall over. All the work that goes into producing a CLI that works, not just that doesn't crash. Some people have problems with that, but that gives you the data that you want as a network operator. It comes with all those years of experience in developing that. All the network management platforms, and then just think about all the features. If you ever read a release notes from iOS or Junos update, look at all the features that are in there that someone paid good money for. That's really what you're buying when you buy the big expensive routers. So the hardware, think of it more as a delivery vehicle, so you don't feel so bad that you just spent millions of dollars and got nothing tangible. It gives you something to hold, but that's not what you're actually buying. Or to use the example from Atlanta, it's like grits are a delivery vehicle for butter and salt. So why do we actually care about SDN? Well, it turns out that some people are good at some things and not so good at other things and try not to act shocked. But if you look at the commodity silicon manufacturers out there, it's interesting that we've hit a state where people can now produce ASICs for literally hundreds of dollars that can do tens or hundreds of millions of packets per second of lookup, but they can't write a good CLI, or they can't write a routing protocol, or they can't even make the box stay up without crashing. Meanwhile, you have a different set of people with a different set of expertise. You have people that know how to write software, know how to write routing protocols. They couldn't fab an ASIC to save their lives. And the interesting thing about the incumbent router vendors who most people buy from is those are the people who have managed to master both. They've managed to hire the right people, acquire the right people, and make sure that they offer both, and that's what you're paying for. You're paying for a reliable router that gives you the features that you want. So what SDN is actually about, it's not about centralizing the intelligence or any one particular method of implementing it. It's really about the threat of getting these two groups together in a way that isn't under the incumbent router vendor. So, is there an actual SDN product out there that will revolutionize anything? If it exists, I haven't seen it. People throw SDN around a lot, and I always take it with an extreme grain of caution. But I want people to think that as a concept, there's actually a lot of merit. Because what you're really trying to achieve is that merging of the two groups. You're trying to break down the wall of the people that make the hardware can't talk to the people that make the software and come up with a reliable product that competes in a way that is outside of what the traditional space is. So maybe someday soon, you'll actually get a slightly less expensive router, probably still big.
Thank you, Richard. Kevin, tell us how you're going to fix this.
Perfect. All right, so I'll just jump right in. My name's Kevin Wollenweber. I'm the Director of Product Management for the high-end routing products at Cisco. So I've been building, I guess, the big expensive routers for the last 15 years that everybody's complaining about. I didn't want to justify why they're expensive, why they're big. I think there's a lot of technology reasons that I'll get into now. But you know, what I wanted to kind of talk about was some of the challenges that we see in the high-end routing space, some of the ways that we are attacking it and trying to make products cheaper. One thing, we are actually going to build a commodity 1RU XR-based switch, or aggregation device. So those technologies are emerging, but actually I really liked your presentation because one of the things that was in there that I find really interesting is, you know, would people feel better if they were paying $1 million for the software and the hardware were free? Because that is where the bulk of our engineers and the bulk of our investment is. So there's a little bit of fudging between hardware and software resources, but yes, there's a lot of investment in software, and for some reason people are comfortable paying for hardware but not software, but the real resource and the real intelligence in those devices is actually in the software. But what I'm going to talk about today is all hardware. So I'm a product manager. I've been doing this for 17 years. You know, one of the biggest problems we have is looking around this room and taking input from every single person in this room, consolidating it down to a common set of features that it makes sense to put into a routing device, and then delivering that to the market. So you guys are probably mostly, if not all, engineers. Engineers are really smart. You could probably, or at least my engineers, can build anything. If I tell them to build a box that looks like this, that's this big and takes this much power, they can build it. The challenge I have is taking all these requests and kind of consolidating them down, mixing that with the technology pieces that I have to work with, and delivering something to market. So one of the things that you can help with, and I think the presentation from Dave and from Craig and everybody else helps me a lot in that I understand what the requirements are. I think one of the challenges, or one of the things that we have to look at, are technology optimization points. So the products you're deploying today are the products that we defined 4 years ago. The products you're going to deploy tomorrow are the products we defined 2 years ago, and the products we're defining today are the products you're going to be deploying in 2015, 2016. So stuff like this, meetings like this, you guys after this meeting bashing me when I'm stuck here in the snow for 2 days, that's where we get these requirements, and that's where we define these products that are going to be delivered over the next couple of years. So I agree that cores are leaning out. I actually don't like the definition of core and edge and aggregation and peering that we defined 25 years ago when we started building routing. These are all shifting. The architectures are shifting, and the needs of those devices are changing. So good, solid input from you and me actually taking that down and working that into product requirements makes a lot of sense here. But technology optimization point is actually slightly different. It's the boxes that I build today, I'm optimizing to leave in the network for 15 years and to have 3 or 4 generations of fabric upgrades. So I'm planning for 28 gig and even 50 gig PAM4 SerDes technologies that aren't even available yet and that will be delivered 3 or 4 years from now. That's built into the devices that you're deploying today. So if we're in a model where, like Craig was talking about, you're going to put something in the network and rip it out 3 years later because something newer and bigger and better is there, I can define the box differently and I can design the box differently. I won't design it for 100 million megawatts of cooling and the ability to put in 10 terabit Ethernet over time. I'll design it at 12.5 gig SerDes, exactly what I'm deploying today, and know that 3 years later I'm going to have a better and more efficient way to deliver that in maybe a slightly different form factor that's not backwards compatible with what we have. So that's part of getting product requirements in and technology optimization. This is one that 10 years ago when we were working on GSRs and early CRSs, we didn't really worry as much about. Power and cooling, though, are top of mind for me and something that I'm focusing a lot on. I'll talk more about it in later slides, but power and cooling is about more than just 10 kilowatts, 12 kilowatts. It's what are you guys going to do with these devices and what environments are they going into? Because again, going back to requirements, the boxes were designed to go into NEBS type of environments, and I've got to survive a chiller failure, and the thing has to be able to run at 50, 55C. Those are requirements that if that changes, if I can design a box that'll never go above 40C or not guarantee operation above that or shut it down, I would be able to design the box differently. And I'll talk about that a little bit later when I get to more of the power and cooling pieces. ASICs are interesting. Actually, I wish Mark was here because I know Mark was going to talk about Moore's Law a bit, so I ripped all that out of my presentation. But Moore's Law is cool. Everybody understands Moore's Law. We can build bigger, faster ASICs. We get double the numbers of transistors. But what most people don't realize is Moore's Law has been broken for the last 10 years in the routing space. Yes, we get more transistors. Yes, we build denser chips. But we don't get twice the number of transistors at half the power anymore. So when I deliver a 100 gig ASIC and then a 200 gig ASIC and then a 400 gig ASIC, the cost per bit is lower, the power per bit is lower, but the aggregate power of those chips and of these devices is slowly creeping up. So if I give you just use round numbers, a 5 terabit box that's 10 kilowatts, the 10 terabit box is probably going to be 12 or 13. So average power or power usage per bit's going down, efficiency is going down, cost is going down, or efficiency is going up, but power per bit's going down. All good things, but the power is sort of creeping up. So one of the things that I've been wondering, and we were talking about a little bit last night, is it better for me to define a power envelope? And you guys say, you know what, I'm going to deploy this in a 12 to 15 kilowatt power envelope, and I should cram as much as that into that power envelope as I can, versus what we do today, where I say, what can I power and what can I cool? Cram that into a rack. And that may turn into a 15 kilowatt rack or a 20 kilowatt rack or a 40 kilowatt rack or wherever we're going. And so I think the design methodology has to change, but that's based on input from the architects building the actual networks. But when it comes to the ASICs, it's funny, the pendulum stuff in the previous presentation really resonated with me because that's what we go through. If you go back to the GSR, and I'm speaking historically because that's where I came from, we had core engines and we had edge engines. And the core engines were bigger and faster and cheaper than the edge engines. You had almost 4 times the capacity at roughly the same cost when you were doing core features and functions versus edge functions. Then, ASICs got going, and we got some really big fast ASICs, and the pendulum kind of swung the other direction, and everybody said, you know what, I want a box that does everything. And that's kind of what we designed in the previous generation and even current generation platforms is I can do core, I can do edge, I can do peering. Maybe there's some software licenses and some things we can trade off, but they're generally about the same size, power, and density. We're shifting back towards a model of, I think, needing very dense, I won't call it core, but IP transport type of devices that have maybe limited FIB, maybe limited features, maybe limited functions. So the stuff I listed here are some of the things that we're looking at in terms of trade-offs in our ASIC families. So bandwidth versus PPS. I can build really big bandwidth systems. If you want them all to run at 64 bytes, that's either going to constrain the bandwidth or force me to build a bigger chip. FIB scale, that's really easy. If I can fit the FIB on chip, it's great. As soon as I go off chip, if I go off chip for 256,000 entries, there's not a whole lot of difference on that board between 256,001 and 8 million FIB entries. Once I put the external memory interfaces in the external memory, it kind of is a fixed cost to that device. Things like queuing, I'll talk about later, but we have started to strip queuing out of the core-based devices. There's no need for 256,000 queues in a 100 gig E that goes from point A to point B and has 8 queues on it. So we've already started to do some of that, and you'll see that more in our next gen offerings. And then buffering. You were talking about what do you need to do in a cheap commodity device versus a larger device. One of the reasons why the cheap commodity device and the small commodity device can be cheap is some of the other functions are done elsewhere. So one of the conversations I want to have and I want to understand is what is buffering by you and is it interesting? It doesn't have to be 80 milliseconds of RTT probably anymore on a big 8 terabit router, but maybe there's some medium between the minuscule nanoseconds of buffering you have in a Tor switch versus what you need on the routing side. And that has direct implication to fabrics and to ASICs. And then the last thing, the one that nobody wants to talk about, but what I was glad to see in Craig's presentation is the optics side of the equation. I could drive, and I won't, but I could drive effectively the layer 3 portion to zero, zero cost in layer 3, and you wouldn't see a huge and dramatic drop from where we are today because of the size and power being driven by the optics. So a lot of the investments we're making today are in the non-sexy things. It's not the bigger, badder ASIC that we keep talking about. It's the power, the cooling, and the optics technologies to drive smaller, lower-powered optics so that you can build these 8 terabit, 10 terabit, 50 terabit systems and have enough plug holes on the front and actually drive the optics off the front of these devices. So you know that electronics are in the ASIC domain, they're in the silicon domain, and we can get Moore's law and leverage it and drive that orange curve down. Optics are taking these step functions down, but they're inherently different technologies. So I think a lot of the investments, I'll show you one slide later, but a lot of the investments we're making in silicon photonics allow us to take some of those optical components into the silicon world and leverage that $300 billion silicon industry to drive Moore's law and actually to drive the optical components to better size, to better power, and allow us to build these dense devices. So a couple more slides just kind of on the hot topics and where we're going, and then I'll take all the tomatoes and knives in the back and everything else. So silicon is growing. I kind of lied to you before. Moore's law helps us. We have a 200 gig NPU now. We're building a 400 gig NPU, and we can continue to see that scaling to 14 nanometer and 10 nanometer and beyond. But it's creating this paradigm where I can build this chip and I can pack a bunch of stuff in this chip, and this chip is so low power for its density that I stack a bunch of those chips onto a board. So the unit power is decreasing, the power per bit's decreasing, but the total power of these devices is starting to go up or continuing to go up. And because everybody will say, I want to build a smaller power or a smaller router, I want lower power, I want lower cost, but actually I still kind of want it to be really big and really dense. What we do is we just pack a bunch of silicon onto that device. So the current shipping product that I manage called the NCS, it's got a terabit line card, and it's an 8 terabit system. I could have built a 4 terabit system at half the power, but instead I wanted to cram as much capacity on there as possible because we're in this bandwidth war between my friends at Juniper and Alcatel and everybody else. We're building the biggest, densest routers we can build because that's the direction we've been given from the field and from the customers. So if that changes, then we're more than happy to oblige and move things around, but that's one of the constraints that we're working under. This is an interesting one to me because it really focuses on that environmental part of things. So this is not actually a router problem. This is a noise, power, cooling, and colo problem. So this is a router. It's actually irrelevant which router it is. This shows what a router does at 25C and what a router does at 50C. So this goes back to the comment I made before. If I need to design a device that goes up to 50C and handles every chiller failure possible and runs through a nuclear war, the chart on the left shows the power draw of the line cards and the fan trays and the switch fabrics and power supplies and route processors and everything else. And so you see the bulk of the power of these devices is the silicon. It's the line cards. It's that 78% number there. That's actually where we want it, because then my focus can be optimizing the power of my ASIC. I can build these leaner architectures we've been talking about, shrink the power of the ASIC, and either build a 10 kilowatt box that's twice as dense or build a lower power device. But the problem I have is what happens when we move over to, I think I have a pointer here. When we move over to the 50C thing over here, if you look, the fan trays in this example drew about 7%. The fan trays in this example drew about 18%. This actually gets significantly worse depending on the architecture of the device itself. So you might see upwards, I've seen some devices that are upwards of 25 to 30% of the power draw of the device is just spinning the fans faster to cool that device. If we can solve that problem, again, we can either build lower power devices, or in that same power envelope, we can build really dense devices. So that's something we've been trying to solve for a while now. And then this is just a historical view of that, kind of looking back at the CRS-1. And remember, there's now 3 different generations of CRS. There's 1, 3, and 10. This is the box that actually shipped in 2004. And you can see that only half the power was used to drive the line cards. The rest was cool, and this is at 50C, cooling the device and the power efficiency of the power supplies and the fabrics. We've done a lot to decrease this in the current generation devices. And this is all looking at the 50C numbers. So you can see that we've gone up about 12.5 times in capacity over the last 10 years. And now we're doing, over 70% of that power is driving the line cards. The cooling as a percentage is roughly the same, but we've been able to obviously use higher efficiency power supplies. We've shrunk that fabric piece down. So we're optimizing the pieces that we can, but this gives you a good sense of looking at it. Like, it doesn't make sense for me to build an RP that's maybe a smaller CPU or less memories, because it really doesn't affect the overall number. The focus really has to be around cooling the device and the line cards itself. This is more of a marketing slide. I apologize bringing it into this, but the point of this is what we're starting to build now in the ASIC front, the stuff we started defining 2 years ago, are families of ASICs. So this, although we call it a chip, is actually a family of network processors. We have 2 versions of this 200 gig chip. We have one that has 256,000 queues and does full HQOS and edge queuing and everything else, and we have one that has 8,000. So we saw this trend 3 or 4 years ago when we started defining these chips. We wanted to build leaner silicon for the core. It's definitely not as lean as what you guys have been talking about and what we see happening over the next couple of years, but we've pulled out things like some of the queuing structures. So you're starting to see these families of chips that we can do high-end, lower functionality, core-based functions, higher functionality, edge-based functions, but with a common packet processing engine in the middle, so I can write the code once. Get common and consistency across aggregation, edge, core, peering, and everything else, but deploy the right set of technology in the right place of the network. You'll see this evolve over the next couple of years in the chipsets we're defining and building today that you'll see in products in the next 2 or 3 years. You'll see leaner variants, you'll see more full-featured variants, you'll see label switching variants with very small internal fibs, but all leveraging some common internal building blocks. That's what we're using Moore's Law for, is not necessarily just to build bigger, badder chips, but integrate more things into these devices. And then I wanted to kind of just finish on the optics piece, and then we'll obviously take any questions you have. This is from some of the guys that are building our silicon photonics, and it's zero correlation to numbers. It's really looking more at trends, but we understand what's happening to ICs and electronics in Moore's Law. We're able to drop the cost per gig or technology down. Every 18 months, we get a new silicon process and we can drop it in. Optics are at a completely different slope. So regardless of where you put that line, the slopes are different and the optics are never going to catch up. So the reason we acquired Lightwire and the reason we're investing in these technologies is, we see optics as tens of years behind electronics technologies. By taking some of those discrete, optical components that are manually put onto boards with coax connectors connected to them, by dropping them into the silicon die itself, I can shrink the size, I can shrink the power, and I can build much, much denser devices. So these are the technologies that are going to enable us to do pluggable, coherent DWDM, or shrink the optics package down to a size of an SFP Plus at 100 gig at very, very low cost and power. So we're investing heavily in these things, but it's going to drive more than just the optics technologies themselves. This is actually a view of something that we're focused on for the next couple years, and I apologize for all the builds, but we think we can integrate optics technologies into the ASIC packages themselves. So instead of having electrical SerDes connecting devices, things move into the optical domain. And so for those of you that understand what's going on the SerDes on these devices, we have on the order of 10 gig SerDes today. 12 and a half on some of our backplane links, but call them 10 gig. The GSR in 1997 had 1.25 gig SerDes. So we've gone up about 10x in terms of SerDes speeds on devices, but the devices have increased, hundreds of times in terms of capacity. So things like the SerDes are starting to become the bottleneck. So one of the things we can do is move from the electrical domain to the optical domain. Everybody wonders, okay, now I have electrical, optical, I can connect them together. My current generation routing devices are going to change. One of the things Dave asked me to talk about was, how do I make sure I'm investing in a technology that's going to be around for the next 10 years? We can utilize these IP or these electrical and optical integrations for more than just replacing backplanes or replacing optics. So I wanted to end on a couple things that we're focused on just to show how these technologies can integrate into even your current generation devices. This is what we call a slice in our data path. Like the 1 terabit card I was referring to before has 5 of these slices. It's some type of NPU, some type of fabric interface, and that makes up a slice on a line card. Today it's a 200 gig slice, and we build these 1 terabit cards by putting 5 of these slices down on the board. The first and easiest thing that we're looking at now is just pure silicon integration. Move to the next ASIC node, take that NPU, take that fabric, lump them together. That's going to allow us to build much more low power and low cost devices. That's already underway, and you'll start to see that as almost a system on a chip or a router on a chip for these next gen designs. But that's still all, everything here is orange, right? This is still all electrical. As we start to look forward at some of these electrical optical integrations, there's a bunch of different things we can do. I think I've heard complaints from probably half the people in this room about optics prices and optics power and optics density. We can start to eliminate some of the optics completely, or develop short reach, very low cost technologies to come off the NPUs and drive external shelves or passive optical devices to get very high density, very low cost optics off of routers. The interesting one that I think nobody really thinks about is I can get rid of my 25 gig SerDes bottleneck here and connect devices together, whether it's through 2 small dies on the same package that are optically connected, or 2 completely individual ASICs with optical interconnects. I can do 50 or 100 gig SerDes, no problem, on the optics space, where in the electrical domain, we're at 12 and a half today, moving to 25 in the next couple of years, and probably moving to 50 and beyond with some advanced modulation. And then the last one, which we will see over the next, say, 10 years, is potentially being able to use optics as fabric interconnects, and either allow you to build, massive multi-shelf type of systems out of smaller building blocks, or eliminate the fabric completely from some of these devices. So this will change the architectures of some of the routing elements. But the other 3 you can work within even our existing architectures. So I crammed a lot in. I see I have about 6 minutes left, so I'll kind of pause now and take questions. But I think most of us will be stuck here for at least the next 2 days. So find me in the hotel or in the bar or something, and feel free to ask me any questions you want.
Thanks very much, Kevin. Yeah, so what I'd like is obviously some audience Q&A. We want to hear what everyone thinks, not only about what Kevin just said, but but what Craig and Richard have said, and obviously what I said. I guess the first question I'd have is for Kevin. Are we being, penny wise and pound foolish for thinking about we want a 10-year roadmap in a device we're deploying versus just being able to being willing to rip it out after, say, 5 years and completely replace it?
So I think a couple things. I think we've been looking at that for a while, and remember, we're building routing devices for everything from the Netflix architecture you're talking about to large service provider architectures that don't change for 10 or 15 years. So I think we need to build devices that last at least a couple generations, no matter what, because we have some people that are going to want to put all 3 generations in, or we might have some people that let's say Netflix misses the first generation of a box, you're going to catch that second generation. So I think we have to have some flexibility, but I think there is some merit to how long these devices need to live, and maybe instead of 20 years and looking at exotic technologies that are 5 years down the road we don't understand, maybe we look to shorten that a little bit, lower the cost of the device. If the cost of the device is lower, I think that plan works better. If the cost of the device is more, you want to sit it in the network and leave it there for as long as you can. So I think there's some of both, and you'll see both in different types of providers.
I watched someone rip a GSR out in Ashburn about 3 months ago now, and it was actually slightly sad but gratifying at the same time,
I have
right?
the same problem. I also still see 7500s in some of the pops I visit, so.
I believe it. Richard, can I call you Richard, or do you prefer Mr. Turkbergen? Okay. So if we think about open flow, open daylight, open big data in the cloud, open whatever, do we need another standards org to attack routing for what you just spoke about? How do we actually move that forward?
Well, I'm not sure that you need a standards org, but it's really unclear where you're going to go with SDN. Right now, it's the promise, the possibility. There's no clear direction as to who is going to come up and say, I know how to write this routing protocol, I know how to write this CLI, I know how to give the features that you want, and then talk to the hardware. That's, I think, where all the effort needs to go, is figuring out the business case for that.
Okay. And Craig, the big question that's on my mind is, what's it like to work for VJ? No?
No comment.
Okay.
Can I have his question?
Yeah, can you have his question? You can have his question, sure. No. So if you have a good answer to this question, why not?
The only thing I would actually add to that is, whether we need a new protocol or not. I think we need to kind of look at SDN and some of the use cases for the data center or software orchestration or WAN orchestration, whatever we're calling it. And if we just look at it like centralized packet forwarding control or service control, I think we can actually accomplish a lot of our goals and objectives, hopefully without inventing something new, because there's plenty of technologies and methods that we can leverage today to actually get us where we want to go if we're just thinking about it like centralized control or packet forwarding in general.
You mentioned in your presentation, you're starting to move the 8075 backbone to 100 gig. What's the biggest blocker there from your perspective?
Power and space. Yeah, it all comes down to power and space, and when we're planning and evolving and trying to implement the roadmap the multiple generations of the network and the topologies, it's being able to put the devices in, whether it's in our own data centers, like I was saying earlier, or in the third-party colos. It's the biggest challenge is taking a big routing node that's now pushing, I don't know, anywhere between 18 and 20 something kilowatts, and going to Equinix or level 3 and saying, here, can you put this in my cage? And they're like, well, no, but you can put it over here in the middle of the floor where there's nothing around it, so it can actually move the air. And so.
Okay. Well, I've got a couple more questions, but we're actually running out of time, so I want to go to the audience. Why don't we start in the middle?
Thank you. Anton Capella, 5'9". Quick question for the panel here. Maybe not too quick, unfortunately, but I'll try my best. The topologies we're describing, especially the N-tiered or N-layered cloths or fabric type things, really seem to borrow a lot from what we consider, or what I would call destination, or destination-based routing, of course. This is an internet-friendly thing. We want to get prefixes places, but maybe there's alternates that make sense in this space. For example, one thing that comes to my mind is MyraNet, where the hosts, the most numerous thing in the network, of course, define what they're going to propagate through. And of course, you have almost no gates to move 10, 40, 100 gigs of traffic. Of course, that's not useful for the internet. So I'm curious, in this space, especially if we want to consider SDN or centralized control planes and so forth, what do you think might happen in that space where if someone could afford to break from the concept of Ethernet and IP destination-based lookups and push that into the edge nodes, would that change anyone's landscape sufficiently or interestingly? Or has it even entered the conversation in anything you've worked on so far? More for Cisco, I guess.
Yeah, I had a feeling. No, I think there's a lot of interesting stuff going on there. If you look at the network function virtualization and some of the things, as you push devices out or push intelligence out and let them make decisions, it will lower the requirements of either the edge or the core devices in that space. And so, a lot of the things that we're being asked for by Dave or by Craig, smaller FIBs or lower functionality devices, or even stuff like segment routing. If you're able to define paths or do, and that's what segment routing is about, is being able to do sort of source-based routing through the network, that will allow us to lower the cost and the functionality of these devices. So I do see that as interesting.
Do you think that'll intersect the rest of the world developing the edge stuff in a timeline that you could even hint at?
I think we will still be building edge routers for a significant period of time. I think it'll take time for those technologies to evolve and allow you to deploy ubiquitously throughout the network. But I'm starting to see pockets of interest there now, which means 12 to 18 months of playing with, looking at, and figuring out how to deploy. And probably in the next 3 to 5 years, I do see large architectures potentially move in that direction.
Thank you.
Thanks. Last question over there.
Leo Bignell, Farsight Security. One of the things I didn't see the panel touch on was sort of the size of the market, and I want to couch that by directing it away from the hardware, because I think we all understand R&D cost and amortized over so many boxes. But on the software side, and I'll pick up on something Dave said just because it was in the presentation, but he mentioned that, for instance, Netflix does not need IPv6 right now in their box. I'm going to assume at some point in the future he does. I don't know if that's tomorrow or 5 years from now, but eventually he will want a box that does it. And that means the vendor, from a software perspective, needs to have, relatively speaking, bug-free software to do that, tested on those high-end boxes, of which there are very few deployed and very few people in this room willing to run the latest and greatest whatever. So whether you need the latest MPLS feature, the latest IPv6, it seems to me that we run into this software development and testing problem where, for years IPv6 was not feature complete on many boxes from many vendors. And so how much does the size of the market constrain what you can do in the software in this space?
I had a feeling with being the one vendor up here, a lot of these were going to come to me. No, so I think two things. One is, although we're talking about LSR-based devices, and Dave says he doesn't need V6, we have to focus on V6 in these devices. They're deployed in a lot of other places, and so we are heavily investing in the V6 protocols and completion of those V6 stacks. But you're right. I think over the last couple of years, there have been so much effort in extending out V4 and all the CG network we have to do, and trying to figure out how to kind of stretch the V4 investment, that maybe we haven't seen that many pure V6 deployments in networks, but it's going to happen at some point. There are going to be people, or there are people today that are asking us for, what can I do in the control planes, whether it be LDP V6 or other things where I can deploy a pure V6 control plane. So we're investing in them and we have them, but I agree with you. Lack of deployments means we haven't potentially found some of the issues that we're going to see over the next couple of years. So we do need to see people either driving in that direction, or we're going to focus the dollars and investment where people are asking for functions.
And to be clear, that was my bullet point was a bit of a troll to see if people were paying attention. We actually have a nice percentage of V6 traffic on our network.
No, absolutely. But I think the point is, and you kind of got there, is that people like Dave, if they don't, or maybe not like him, who don't have IPv6 deployed on some level, have to fund the development of that. So it's there when they need it, and they fund that by buying boxes today that go back into your R&D thing, right? So
But we do have enough deployments of V6 and enough people asking for everything in V6 that in the high-end devices, you're going to see a heavy dose of V6 support across the board.
So the one other thing that I would say is, Craig's number one issue is the power and density in space. My number one issue is probably software stability, with power and density being number two. So to Leo's point, when all of us are out there asking for features, asking for weird, bizarre features that apply only to us, that make the software ridiculously complex, I think that's probably the biggest driver to us not getting what we want in a timely fashion.
Absolutely.
Yeah, I think the funny thing about that is I would almost complexity is good. It drives vendor differentiation. It allows us to do things that potentially you don't have in other devices. But the simpler I can make these devices, the more solid I can make it, and higher uptime, better resiliency, and not going down. Those are all good things for us because then my support load on the back end goes down, and I can actually spend more engineering resource on features, functions, or stability and infrastructure. So I'm fundamentally completely okay with simplifying these places in the network because it allows me to invest in potentially other areas or hardening the infrastructures of the devices we have. So it makes sense.
Give the last word to Taz.
Yeah, last thing I'll say about that is, the point about the size of the market and where the vendors are investing is a good one because one of the things I was saying, it's not that these features and functionality or the functionality itself goes away. It's just that we're saying if you can fund a big development shop and you have a bunch of software developers, you can actually move that into a software development shop, do the ROI and the cost benefit analysis and say, I can do it at the application or the software layer better, faster, cheaper, and iterate on that. And then that gives me the ability to dumb down the network device. Kevin might have a long tail in this room of people that still need him to develop those features and functionality. So it's a trade-off.
Well, thank you very much to my panelists. You guys did a fantastic job. I really appreciate the candidness from everyone. Again, sorry that Cisco ended up being the target. It was never the intention, but thank you very much. And thanks, Taz, and thanks, Richard.